So here's a quick little review video on how to draw Lewis dot structures and then figure out VSEPR shape from the Lewis dot structures. So when we're looking at transfer of electrons, those are ionic bonds. Beryllium has 2 valence electrons. Oxygen has 6 valence electrons. And what's going to happen is these 2 valence electrons on the metal beryllium are going to be transferred to oxygen. That's going to result in a lovely beryllium cation that has a positive 2 charge and a lovely oxide anion with those 2 extra electrons has a charge of -2, and then these guys are going to stick together because opposites attract. Same thing here, magnesium's a metal, fluorine is a non-metal, so we have another ionic bond. Magnesium has 2 valence electrons, fluorine has 1, 2, 3, 4, 5, 6, 7. So we're going to go ahead and transfer one of magnesium's electrons to fluorine. Fluorine now has 8. The problem is magnesium has 1 more he needs to get rid of. So what we need is 1 more fluorine. 1, 2, 3, 4, 5, 6, 7. And then that, let's see, it's a different blue. This other valence electron will be transferred to that other fluorine, resulting in a magnesium cation that has a charge of +2 and 2 fluorine anions that each have a charge of -1. -1 minus 1 plus 2 balance out to that 0 that we're looking for. So these guys are now all covalently bonded molecular compounds. They're going to share electrons. So what we do here is we first count the valence electrons. Carbon has 4, each one of these hydrogens has 1, and oxygen has 6. 6 and 2 is 8. 8 plus 4 is 12. We have 12 valence electrons that we need to share amongst these atoms. Hydrogen is never going to go in the middle. Oxygen is more to the right than is carbon. So carbon's going to be our middle guy. And then we're going to put hydrogen and oxygen around the carbon. Carbon is almost always in the middle. Carbon enjoys being in the middle. So now we're going to start drawing our electrons between our atoms. So there's 2 and there's 4 and there's 6. I could continue 8, 10, 12. I've used up all 12 of my electrons, but this is a problem because carbon only has 6, 2, 4, 6. So what we're going to do is erase one of those pairs on the oxygen and move it instead to a double bond shared with the carbon. So just double count our electrons, 2, 4, 6, 8, 10, 12. And we can draw a Venn-like diagram just to make sure oxygen's got 8, carbon has 2, 4, 6, 8, and each hydrogen only has 2, but that's okay, remember that hydrogen only has that first energy level, which only has space for 2 electrons. Let's do nitrogen. So nitrogen each has 5 electrons. There are 2 nitrogens, so that's a total of 10 valence electrons. So we have our 2 nitrogens. There's no one to put in the middle since there's only 2 things. And we're going to count a 2, 4, 6, 8, 10. He's got 8. He only has 4. So I'm going to go ahead and erase and give them a double bond. So he has 2, 4, 6, 8. He has 2, 4, 6. Closer, but we're not quite there yet. So I'm going to erase another one of those pairs. And we're going to share a third chunk in there. So now he has 2, 4, 6, 8, and this nitrogen also has 2, 4, 6, 8. This is a 1, 2, 3 triple bond. This guy was a double bond, and of course these are both single bonds. Carbon tetrachloride, CCl4. Carbon's going to go in the middle. He's got 4 valence electrons in the middle. Each of those chlorines has 7 valence electrons. There are 4 of them, so we've got 28 plus 4 is 32. That's a lot of electrons. So there's our carbon. We're going to put our chlorines around the carbon, and we're going to go a 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Perfect. Everybody's got 8. Let's look at this guy, nitrogen triiodide. Nitrogen each has 5 valence electrons. Iodine each has 7. There are 3 of them. 21 plus 5 is 26. Nitrogen is more to the left in the periodic table, and also there's only 1 nitrogen and lots of iodine. So we're going to put nitrogen in the middle. We're going to put iodine around nitrogen. 26 valence electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. There's our Lewis dot structure for Ni3, nitrogen triiodide. Last but not least, we've got water. Each of those hydrogens has 1 valence electron, plus oxygen has 6. 6 plus 2 times 1 is 8 valence electrons. Oxygen is going to go in the middle. Hydrogen will never, ever go in the middle. We're going to share pairs between oxygen and hydrogen first. Hydrogen is already happy. Hydrogen is good with 2. So there's 2, 4. We're going to put our last 6 and 8 here on the oxygen. So I would say that oxygen has 2 non-bonding pairs of electrons, and then of course 2 bonding groups. So now we're going to apply that idea of Lewis dot structures to VSEPR theory. VSEPR stands for valence shell electron pair repulsion. Valence shell electron, those electrons that are in the valence energy level, that valence shell, and then those pairs of electrons repel each other. They push away. They try to move as far away from each other as possible. So this guy we drew on the last screen. We've got 1, 2, 3 bonding groups. Even though that's a double bond, it's still just a bond. It's just 1 double bond. So with these 1, 2, 3 groups of bonds, that's going to be trigonal, triangle, but it's going to be flat, planar. So this guy is going to be C. It's going to look like this guy, where we've got carbon, oxygen, hydrogen, hydrogen. So I'm actually going to skip over to this one. So NH3, this is ammonia or nitrogen trihydride. And it's a little bit different because even though there's 1, 2, 3 bonding groups, there's also this pair of non-bonding electrons. What happens is we have that 1, 2, 3 bonding groups. So this is our nitrogen, hydrogen, hydrogen, hydrogen. But this pair of electrons is sitting up here taking up space, which pushes those hydrogens down a little bit, forming, instead of a flat triangle, I now have a triangular pyramid, trigonal pyramidal, and then this guy was planar. Good, let's look at CO2. CO2 is pretty easy. I have 1, 2 bonding groups. There are no extra electrons on the carbon. So these guys are going to push each other away, and they're going to be a line, and we're going to call it linear. And it's going to look like this. So even though this isn't CO2, clearly, because there's only 2 atoms instead of 3, our carbon dioxide molecule would still be in a linear shape, 180 degrees from oxygen to oxygen. Water is a little bit different here. So water, it looks like we should have a line like that. But what happens is this. I've got these 2 extra pairs of non-bonding electrons. They take up space. They push those hydrogens down a little bit. And so instead of being a straight line, we now have a bent line. Water has a bent geometry. And it's going to look like this. Because there's a pair of electrons here taking up space, pushing that hydrogen down. There's a pair of electrons here taking up space, pushing that hydrogen down. Which leaves us with tetrahedral. Tetrahedral must be this guy. So there's a game called Tetris. In Tetris, there are things, these shapes that each have 4 blocks. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Tetra is 4. So tetrahedral, there are 4 things stuck to the central atom. 1, 2, 3, 4. This is tetrahedral. This looks like a plus shape. It looks like it should be flat, but in reality, in three-dimensional space, what happens is they spread out a little bit. And so we have one thing that kind of points up and all the other ones kind of go down. But if we measured the angle between any two of those atoms, it's always going to be 109.5. 109.5. Between here and here, 109.5. Here to here, 109.5. So this guy is going to be called tetrahedral, tetrahedral, tetrahedral. Let's do one more slide. Lots of the same ideas that we just looked at. So carbon, tetrachloride. We're going to put carbon in the middle. It's got 4 valence electrons. Chlorines each have 7. 7 times 4 is 28. 28 plus 4 is 32. Carbon in the middle. Chlorine all around. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. There are 1, 2, 3, 4 things stuck on the carbon that makes this tetrahedral. This one, BH3, boron, has 3 valence electrons. Each hydrogen has 1. 3 plus 3 times 1 is 3, is 6 total electrons. I'm going to put boron in the middle, hydrogen all around. 2, 4, 6, that's it. This is one of our exceptions to the octet rule. I'm going to have boron, and I'm going to have 3 hydrogens. There's no extra electrons on the boron. That's it. There's just 1, 2, 3 bonding groups. That makes it a triangle, but it is a flat triangle. That makes it trigonal planar. It is trigonal planar. It is flat. As opposed to this guy, NH3, nitrogen has 5 valence electrons. Each one of those hydrogens has 1. 5 plus 3 times 1 is 8 valence electrons. I'm going to put nitrogen in the middle, hydrogen all around. 2, 4, 6. I've got one more pair to get to 8. It's going to go there. So even though these two guys look similar, I've got boron with 3 hydrogens, I've got nitrogen with 3 hydrogens. The difference is that most amazing, it's so amazing, it needs another color, pair of non-bonding electrons. This pair of non-bonding electrons on the nitrogen is going to push those hydrogens down. And so instead of having a flat triangle, we're going to have a pyramid. So still a triangle here on the bottom, but instead of being flat, it makes a little bit of a pyramid, which means that this guy is trigonal pyramidal. Not flat, but a little bit pointy, because once again, I've got a non-bonding pair of electrons sitting on top of that nitrogen. Let's look at water. Water was that quirky guy. We put oxygen in the middle, hydrogen all around. Oxygen has 6 valence electrons. Each one of those hydrogens has 1. 2 times 1 plus 6 is 8 valence electrons. 2, 4, 6, 8. So you'd think that this is a line because I've got oxygen, hydrogen, hydrogen, but it is not, because these guys push and these guys push. And so this ends up being not a line, but instead it is bent. Those 2 non-bonding pairs of electrons bend that water molecule. That shape is going to be bent. Which leaves us with Br2, Br, each has 7 valence electrons, times 2 is 14. There's really no way to put 2 Brs except next to each other. 2, 4, 6, 8, 10, 12, 14. I've got these 2 Br atoms stuck together. It's gonna be a line. Everything that is diatomic, 2 atoms, Br2, Cl2, O2, all these guys, I've got just 2 atoms, have to be a line. Whoa, I missed. And so that is the end of our little chunk of VSEPR and Lewis dot review. Good luck on that test.